Hello. Hi. So the first section of this week will be finishing off what we left last week to reformulate the scattering theory, or I call it the luxury version of scattering theory. Remember what I did last week is to work on the Feynman diagram with external lines of the mesh shell. We call it a green function of mesh shell green function. And we come up with two answer or two significance or two meanings of these functions. First, all by introducing a source into the interaction. By introducing the source into the interaction and calculating the so-called vacuum persistent amplitude for a vacuum to evolve into a vacuum in the long future, and we can define a generating function now. A generating function now for the source, and if we got an answer 2 and answer 3. For answer 2, I work in the interaction picture, in which we treat the interaction Hamiltonian, original interaction Hamiltonian, and the raw phi as our interaction. And then we can come up and calculate this thing, and you will see that all the diagram will appear as this. And therefore, every point represents a source. Therefore, I can expand or express this transition, the persistence amplitude as a series containing rows to the certain order and the corresponding green function. And these green functions are the sum of all the Feynman diagram. That's the first meaning. The sum of all the Feynman diagram will give you the green function. And then you can go back to the detail. And there's another meaning for this green function. I can also work in the Heisenberg picture of the whole Hamiltonian, that is excluding the source. You can see it here. So if I work in the Heisenberg picture of the H, except for the rho phi, the source term, and then I can after some calculation give you that the same vacuum persistence amplitude will give you the same generating function now, but now the green function is a series of phi h by time ordered and sandwiched between two real vacuum. Because I'm working with the Heisenberg picture of H, so this vacuum is the true vacuum, the whole vacuum of the Heisenberg pic of H, instead of in the first, in answer 2, the answer 2, the 0 is actually in answer 2, it's a different thing. Okay, and now, so this is, I told you that time, this answer, this green function is very, very important, not only for the particle physicists, but it is also very useful for the application of quantum field theory in condensed matter theory. Okay, so now let's back to, then the question then is whether answer 2, working in the interaction picture, the same as answer 3, which we get by working in Heisenberg picture. Presumably they should be the same, and that's the idea. So if they are the same, then we can calculate this complicated abstract green function, but very, very useful green function in terms of the Feynman diagram. Okay, that's the key idea. Okay, so with this in mind, we go back to the reformulation of a scattering theory. The point is now I don't need to introduce anymore the turning on and turning off function f in our exposition. Okay, so yeah, here Coleman give you a very short summary of what the theory will look like. What the basic assumption? Sorry, the basic assumption of this reformulation. And here we talk about H. That's the whole Hamiltonian. But now the turning on and off function is gone for good. Okay, and with this whole Hamiltonian, we have some basic result. For example, there will be a vacuum and subscript with P, which is physical. So this vacuum, the physical vacuum, is the vacuum of the whole H instead of just the H0. That's a very key difference. We will see the difference will appear later in our exposition. And then, as before, I can define the generating function of source by adding a source to Hamiltonian, and then calculate the vacuum persistence amplitude in the presence of this rho. But remember, now the theory is working in the full Hamiltonian. Therefore, it is vacuum P, physical vacuum, to persistence in the long future, still as physical vacuum. And then if you expand this amplitude, expand this generating function now, you can get all the green function. And in this way, the green function is the time-ordered product of a series of phi h. Again, remember we are working in the Heisenberg picture, so that's why it's phi h. So the time-ordered product of a series of phi h Heisenberg operator sandwiched between two physical vacuum. Now the question is this definition, and obviously this definition is the answer 3. And the key question, of course, Coleman pointed out in this reformulation first, is answer 3 equals to answer 2. Remember, answer 2 is the green function defined as a series of Feynman diagram, and it's calculable. So if 3 is equal to 2, answer 3 is equal to answer 2, then we got a tool to calculate these abstract objects of green function. And question 2 is this green function, if taken on shell, related to the S matrix? So if you can answer 1 and 2, then you can calculate the S matrix. Yeah, because if the S matrix is related to the green function and the green function is related to the Feynman diagram, you got a tool to calculate the S matrix in terms of the green function, in terms of the Feynman diagram. Okay, so first, now let's answer the first question first and the second question second. The first question is answer 2, the same as answer 3. Now let's first rewrite the answer 2 into a more precise form. Remember, answer 2 is working in the interaction picture. Interaction picture means you treat the original interaction, I call it H prime, and rho phi as the interaction Hamiltonian. And therefore, there is a very simple, if you calculate in this way the 0 to 0, the vacuum to vacuum persistence amplitude, then you got this result. Okay, because this is in the middle. I have a expression for the S matrix, which is the exponential of interaction Hamiltonian. Again, remember now the interaction Hamiltonian consists of the original interaction and rho phi, the source interaction we just introduced. So this is a very standard Dyson formula I have already talked about 2 weeks ago. So this is S and persistent amplitude between vacuum and vacuum. So if you expand this, you got the Feynman amplitude. You got the Feynman diagram. Okay, but but at this moment, I have to take out some of the vacuum diagram. For example, this is the S metric, the persistent vacuum persistent amplitude, the leading order of the persistent amplitude. Here, for example, to the order of rho square and to the order of G square. G square means there are two interaction vertices. Then it could include this diagram. That's fine. However, it could also include this diagram. And in this diagram, you see that this part is not related to the source. It is actually, we call it a vacuum bubble. That means there's something happened in the vacuum. It is going to happen anyway, whether you have a source or not. So this part, the vacuum bubble, is not related to the thing you want to calculate, and it happens anyway. So usually when we say we calculate in Feynman diagram, these parts are excluded. So we only include the Feynman diagram without we call vacuum bubble. So to take out the vacuum bubble, you will divide what we have here. Here we have vacuum bubble is included, subtract it out, or is divided by all these vacuum bubble. You can see that the vacuum bubble is the multiplication to the real diagram. Okay, so therefore I can use this S to S, the vacuum to vacuum persistent amplitude without source. This will be this persistent amplitude will include all the vacuum bubble. So by dividing the persistent amplitude with source by this without source, I get rid of all the vacuum bubble diagram. Okay, so that's the idea. Okay, so with this in mind, then I can expand this ZF, the generating function now, and get all the green function. But here we need to be careful. This green function is the Feynman diagram. That is, by getting the expansion, the green function will give you this. Okay, by taking the nth derivative of the rho, and every derivative will take down a phi I. So if this is nth order of the green function, then we have a n phi I in front of the exponential function. Okay, therefore, I hope you are convinced yourself from this generating function. Now we can get this. And then this, therefore, the green function of Feynman diagram without vacuum bubble is defined in this way. Okay, so that's the first step. Now I have succeeded in writing the answer 2 into a more precise form here. Okay, second, next I want to relate this thing to the green function in the Heisenberg picture. So what I did is to transform this phi I into the phi h, the phi in green function. So before I proceed, let me remind you, phi I and phi h are actually very easily related by sandwiching the phi I between two ui, between two time evolution operator. Okay, so you can check out this formula in the earlier exposition. And however, you can see that this UI is the time evolution operator. You can get a formula here. So UI is actually the time evolution operator between two time is actually related to the exponential function of the integration of hi between these two time. And this exponential function is applied here. Remember, here we have a time the integration of hi between the initial time and the later time. So I can divide this whole thing into one segment, and one segment, and take one segment to each of the product. And remember, this is time order. That's the key. If it is a time order, every piece will fall into the place which is between two times. For example, inside this, we have a UI evolution from T1 to T2. And this T1 and T2, due to the time order, it must be between phi I x1 and phi I x2, because all the h has time between T1 and T2. So according to time order, it must be put here. Okay. So is every other time exposition. Okay. So now this phi I, so I hope I convinced you that this time evolution operator should be divided into one section, two sections, between sections, and put into their rightful places. And when they are put into rightful places, this UI could be written again as the product of this UI TA0 and UI 0 TA. Okay, this could be written as this. And if you plug this formula into this place, then this part could couple with this, like here. Okay, and the other part could related to this phi I, and the combination will give you phi h. Okay, it is a little bit awkward to say in a lecture to say this in a lecture. However, if you sit down and take a look carefully, you can see that the formula is not very long, and if you just need to remember all the relation between the interaction picture and the Heisenberg picture. Okay, so if you do this, then it is very easy to show that the numerator it could be written in terms of a series of Heisenberg picture field operator phi h x1, phi h x2. Remember, all the UI has been absorbed into these field operator. Just two evolution operator are remaining, that is at the beginning and at the end of the whole series. Okay, so we got this formula for GF. And next, I'm going to show that this is related to phi h, the green function I want to show. Okay, it's not that difficult, but however, this is the most mathematical part of this presentation. By looking at it, best to look at this UI 0 t minus 0. Okay, so by working on this state, of course here Coleman put this thing and you put all the other things as defined it as phi. So that is from here on we call it phi. But it is only to show you that at the end only the vacuum will contribute. So this phi could be anything. But here it denotes all the rest of the expression. So this whole thing could be written as phi ui 0 t minus 0. Okay, so we want to see how this time evolution operator will give you when time t minus is sent to minus infinity. That is means you send it to the long past. And what Coleman did is to create an exponential IH0 t minus, okay, because T0 H0 is equal to 0, because here there is a vacuum, and this vacuum is the eigenstate is the vacuum of this H0, so this is equal to 1. But if I write it here, then this and this will give you the Schrodinger picture. And in the Schrodinger picture, I can insert a whole series of all eigenstates of the full Hamiltonian. That is 0p and p0, n, and take a sum of it. Okay, so all the other eigenstates will contribute here, and vacuum will contribute here. The key is that the vacuum is always separated from all the continuum of the other eigenstates. Later, this integration will give you 0, but that's later. Okay, so the only thing you need to remember is the vacuum is separated from the continuum of other eigenstates. Okay, so I can insert a 1 identity operator, which is equal to a projection into all the possible states. We usually say that this is a projection to any possible state. And then, therefore, there is a contribution here, and a contribution of this touching this. Okay, and because this U0 t minus acting on 0 is 0. Okay, so because this is vacuum, so we'll get phi 0p and p 0 0. Okay, plus when U0 t minus acting on the n, then this n will becomes exponential IEn t minus. That's because n is the eigenvalue. N is the eigenvalue of the whole Hamiltonian H. Okay, and the U could be written as exponential IHT. So when exponential IHT minus acting on n will give you exponential IEn t minus. And while this acting on this vacuum, it will give you exponential 0, and exponential is of course 0 is of course equal to 1, and therefore this will be reduced to phi 0p with 1 we can disappearing, and here there is a p0 and connect with this 0. And here you can see that the difference between the physical vacuum and the vacuum of the H0. So you have to be careful about these notations. Okay, so the key observation is that when this T minus goes to infinity, where's the sentence? I think when when you do this integration and let T minus equal to infinity, then this exponential function, because it's an exponential function of imaginary number, then it will oscillate. So when you do the integration, not because T minus equals to infinity, it's because when you do this integration, then this will vibrate rapidly because T minus is a large number, negative large number. And therefore, when you do this integration, the whole thing will cancel out with each other. Okay, so therefore, the second term simply vanish when T minus is sent to the minus infinity. Okay, so I think there is a theorem about this. This is called Riemann Nebescu lemma. Okay, I'm not familiar with the mathematics, but we usually use it in physics. especially mathematical in physics. Okay, so the bottom line is only the vacuum, the physical vacuum, will contribute in this, and the rest will simply vanish after you take the time t minus to minus infinity. Okay, so that means again, oops, sorry, I lost my track. Okay, here. So that means when t minus goes to infinity, you only need to consider, you can sandwich here a 0p and p0, okay? Likewise, when this t plus is sent to infinity, the same thing could be argued again. And on that side, we also could insert 0p and p0 in between the zero, the fake vacuum with the rest of the formula. Therefore, again, when this goes to infinity, you sandwich in 0p, p0. And when this goes to infinity, you send in the p0, 0p. Then you got this formula. Okay, so 0p, p0, 0p, p0. So that's the result of sending this part is because you send the t minus to infinity, and this part is the result of sending the t plus to infinity. Again, all the rest of the continuum is washed out using Coleman's word. It's washed out because you are taking this limit. Okay, they oscillate so fast they don't contribute. Okay, so the bottom line is you got this formula. Now I have transformed the zero, the fake vacuum in the original formula into a physical vacuum. And now the physical vacuum is acting on the Heisenberg picture of the field operator. Remember, this is exactly I want. This is exactly I want, the final result with the addition of this and the addition of this. However, these two we can cancel out from the bottom of the formula, because at the bottom of the formula, I can do exactly the same thing as before. By sending t minus to infinity, I sandwich here a p0, 0p, 0p, p0. And by sending t plus to infinity, I send in a p0, 0p, and therefore that's it. 0p, p0, 0p, p0. Okay, so exactly the same thing. However, by including this denominator, this and this cancel out, this and this cancel out, and the physical vacuum and physical vacuum actually is normalized to 1. Finally, we got our result. All the rest are canceled out, only the green function is left. So GF is equal to G. Remember, GF is the sum of all the Feynman diagram excluding vacuum bubble. Now it is shown to be equal to the green function of Heisenberg operator between true vacuum. Okay, so it's cute. Although some of the argument, it probably is a little bit awkward for me to do online. However, I hope you enjoy it when you read it in the PowerPoint or in the lecture notes. Well, but bottom line is very simple, that the answer 2 and answer 3 are the same. Okay, here I also include in my PowerPoint exactly the same exposition from Tong's lecture notes. You can check in between these two explanations and to get a deeper understanding. But you can see that actually they are exactly the same arguments. Okay. Now, so number 2 and answer 2 and answer 3 are exactly the same. So the two questions, the answer to the first question, the answer is yes. Now, the second question is this green function related to the S matrix? So this is a little bit more complicated. Okay, a little bit more complicated. The answer is this. Okay, this is called the LSZ reduction formula. I'm not going to prove on the screen. And actually, you can find a proof. Tong does not include a proof. However, Coleman has proved it in his lecture notes in very, very detailed and very clear form. So if you are interested, you can check out Coleman's lecture notes. However, let me remind you something which is very important, and some of them we will use again later. So first, the green function as we defined, again, as we defined here, the green function actually include the external line, the propagator for the external line. Remember, we use a source to generate this external line. However, in this Feynman diagram, originally these are external line. However, in this calculation, they become internal line. Therefore, there will be a lot of k squared over minus square, the inverse of it. Okay. Therefore, when we put all the external momentum on shell, remember the external momentum should be on shell to give you the right S matrix, because in actual scattering experiments, these K should be online because they correspond to real particle. Okay. However, if I put them on shell, then this propagator will vanish, or will explode. Sorry, the propagators will become infinite. Therefore, in this formula, we need to multiply these green function with the inverse of the propagator. By inverse of propagator, I mean k squared minus mu squared. So you can easily see that this is the inverse propagator, inverse propagator, and they will cancel out this propagator. In technical terminology, they are usually called truncated. Truncate means you cut off this, cut off this, cut off this, cut off this. Or you can put it more simply, you remove the propagator of the external line. That's the key. Okay, so that means the green function needs to be truncated at the external line by multiplying this k squared inverse of the propagator. Secondly, and even so, the answer is only almost. As Coleman explained in his lecture, here I list his explanation. The reason it is almost is because the field phi, which enter the formulation of the green function, may not have the right properties. By right property, he means that the vacuum expectation value of phi needs to be 0, and the creation operator, the phi will create exactly one particle instead of multiplying by a coefficient. Look, remember this field is not observable, so therefore you can rescale this phi by multiplying it with any factor. We usually call the rescaling factor Z3. By multiplying the field into a new operator, we didn't change the physics. We didn't change the physics because we multiply all the phi, and the result will be simple because you just can take out the z from your formula. However, so that means phi could be rescaled as you want. Therefore, but on the other hand, if phi can be rescaled by anything you want, then it does not guarantee this phi will have the right property of creating exactly one propagator with the right normalization. Therefore, eventually, after all, these phi are field operator in the Heisenberg picture, so their normalization had to be adjusted carefully. Therefore, Coleman defined a Z3, which is the rescaling factor, by calling phi acting on 0 multiplied by k. And therefore, if phi create exactly one particle, then this must be equal to 1. But if not, this factor needs to be rescaled from the phi to get a phi prime that has the right upper condition. Okay, so therefore, Coleman will define a renormalized green function, which is the green function for phi prime. This phi prime is rescaled, is a renormalized or rescaled field operator defined as here, that will satisfy the condition of the vacuum spectrum value equal to 0. Very good. And the phi prime sandwich between 0 and k equal to the exact plane wave as we expect from the free picture, the free interaction picture. Okay, so these two will become conditions we want to impose on the field theory so that we get the right green function that will give you the right S matrix. Okay, so remember carefully these two conditions, because they will become the renormalization conditions we'll encounter very soon in the next couple of weeks. Okay, so if we rescaled it and have these conditions ready, then Coleman can proceed to prove the LSZ formula correct. That is here. That again, that is the green function of this renormalized field operator multiplied or truncated at external line will be equal to the S matrix. Okay, so this is called the Riemann-Zimmermann reduction formula, and the proof is not very complicated and actually very entertaining. However, I don't have time and to do it online. Sometimes it's very awkward to do it online, but let me just quote the final result, and it's very, very simple. Okay, so this is green function truncated and then put online. Of course, it is renormalized, rescaled to satisfy a good condition, and then it will be equal to the S matrix as we expected. So the bottom line, let me list it here. The bottom line is simple. The S matrix element, according to LSZ, equals to corresponding green function with external line truncated, or I should add on-shell green function with external line truncated. Okay, and remember the answer, the question 1. Answer to the question 1 tell you that the green functions equal to the sum of all corresponding Feynman diagrams. So what that means, if you put these two things together, that means the S matrix element will be equal to the Feynman diagram. Okay, so the bottom line is very, very simple. What we had in low budget scattering is still correct in luxury scattering theory. So that's why I didn't want to put too much time in luxury scattering theory, just outlined it, because the bottom line is the what is correct in low energy, in low budget scattering theory is still hold in the luxury scattering theory. Okay, so let me put it here. This is the end, I think. Yeah, that and this is the exposition from Tong's lecture notes. So that's the end of this section, because here we finally explain the low budget scattering theory and the luxury scattering theory and show that they are the same. Okay, so I hope it is useful. Next, I would like to talk about propagator and then go on to talk about renormalization.